Hello and welcome to one more challenge with these Codility lessons. Today we are solving the Fibonacci Frog exercise from lesson number 13. So we are given an array of numbers representing positions where we have leaves, and we can imagine there's a frog on one side of the river, which purpose is to cross to the other side of the river, maybe in one single big jump or through smaller jumps on these leaves. However, the frog can only jump a certain fixed number of positions at once, and these are indicated by the Fibonacci numbers. In other words, the frog can jump either 0, 1, or 2, or 3 positions, 5, and so on at once in one single jump. And the purpose of the exercise is to find the minimum number of jumps within which the frog can reach the other side of the river. In this example, the first possible jump is starting at position -1. This is specified by the problem description. And we can jump 5 positions at once. We have a leave here at position number 4 with index 4, which means we have to jump 5 different positions starting from -1. And as it happens, 5 is a Fibonacci number, so this jump is allowed by the frog. And then the second jump to the different leave is skipping 2 positions. So we have 2 positions here, and 2 happens to be a Fibonacci number, so we can allow this jump. And this last jump is of 5 positions again to cross beyond the highest number or the highest position of our array to reach the other border of the river. So it's very important to keep in mind that we are starting at position -1 and we are ending or crossing the problem at position size of the array +1. We might want to think that after the first jump at this particular position here, we can look for one big jump, and this in total would provide us crossing with 2 big jumps. Like the first one is 5 and the second one is 7 positions. However, 7 is not a Fibonacci number, so in this case we can't allow the frog to cross from this position here to the other border of the river in one single jump of 7 positions. So for this example that is provided in the problem, we have a total of 3 jumps to cross to the other side of the river. And this is the minimum number of jumps that the frog can make in this crossing. The way we will solve this is the following. First, we are going to define a new array where we will store the number of jumps required to reach each particular position. However, we are only interested in positions where we have leaves. And we are going to start by identifying the leaves that we can reach within one single step at first. And this would be this particular leaf. So we have number 1 here, which means we have a leaf at this position. And we can reach this leaf jumping 5 different positions, and 5 is a Fibonacci number. So we are going to put 1 in our newly defined array, which means that this particular position, there is a leaf and it can be reached within one single jump. And in this particular example, we only have 1 leaf which satisfies these conditions. The second step is that we are going to try to find the other leaves that we can reach within more than a single step. I mean, you need more steps to reach a particular leaf. Our final purpose is to have in this array for each position the minimum number of steps or jumps that are required to reach each single position. And the way we are doing this is that every time for each leaf, we are going to check if they are separated by a Fibonacci distance from a previous possible position. Let's go through the details and see how it works. For example, the first case is this particular leaf here. So at first, this index here is 0. This leaf is at index 3. And then we are going to do this particular position minus the first Fibonacci number, so -1 position. And in this case, we don't have a leaf here. And this index is also 0. So it's not a valid case. Then we are going to check another one. It's also number 1. Then we are going to check number 2. So if we consider we are jumping to this leaf from a previous position within a distance of 2, it's not valid because we can't do it. Here we don't have a leaf either, and so on. We're going to test number 3, neither. And number 5 is going to lead us to somewhere in the negative indexing. If it's something less than -1, it's way beyond the boundaries of our problem, since we are starting at position -1, so we're not allowed to go to -2 and -3. So in conclusion, this particular position, this leaf, can't be reached using Fibonacci jumps. Now we can move on to the next leaf, and we're going to apply the same operation. We're going to do backward distance with one jump, one Fibonacci distance, then the number 1 again, then the number 2 if we are skipping 2 positions backwards. And here we have a leaf that is within a Fibonacci distance from this particular position. So this is a potential case where we can consider first the frog is jumping in one jump up to this position and then to this position, and therefore we can insert number 2 here because we need 2 different jumps to reach this position. However, we are looking for the minimum number of jumps for each particular position. So we are going to continue in our algorithm to check the other higher Fibonacci numbers to see if there is a faster way to reach this particular position. So we are going to test at the end the number 8, and we reach an index of -2, which is outside the boundaries of our problem. Remember, the first position is -1, so -2 is not allowed in the problem. So there is no faster way to reach this position unless we jump first 5 positions up to here, and then we jump 2 positions up to this leaf. And in this case, we are going to insert the number 2 here because this position can be reached within 2 different jumps. Then we're going to do the same thing for the end of the array because we need to cross to the other border, and this is considered one additional leaf. In fact, when we will write our code, we are going to add one additional element at this position to simulate the presence of the other border of the river. And by doing so, we can see that this position and this position are separated by 5, and 5 is a Fibonacci number. So we can jump one last jump to reach the other side of the river. And in total, we have 3 because we are adding 1 on top of these 2 jumps. As you can see, it's not the simplest of the solutions we have seen in this playlist. And if you want to go further on such search algorithms, you might want to look for the breadth first search versus the depth first search algorithms and other similar approaches for searching algorithms. But this in itself is a full course. We can't cover it in this video. So we're just going to jump into C++ and Python and see how we can write all of this. So this is our solution in C++. It's the solution function. It takes a vector as a parameter. And as we have said in the algorithm section, we are going to push back, meaning adding one leaf at the end of our array A, the vector A, because we need the other border of the river to be present in our numbers as an allowed position. Then we are going to compute the Fibonacci numbers. So this part here is simply to compute all the Fibonacci numbers that we are going to need. We are limiting our search to the numbers that are less than the size of A because we're not going to jump further than the full width of the river. And just so you know, it's important to put a float here in the vector because for the performance tests on Codility, if we put simply integer, it seems that some numbers cannot be contained anymore as an integer type, and it's going to cause us troubles in the testing. Then we are going to erase the first 2 elements of the vector of Fibonacci numbers because these are 0. Then the second one is a jump of 1 position, which is also repeated in the third element, which is also 1. So we don't need the first elements 0 and 1 because the rest is going to be enough for us. And then we are going to declare our new reach steps array that we have described in the algorithm section. It's the same size of A, and for the moment it's full of zeros. It means that at this point of our program, all the positions can be reached with 0 jumps. Then we will start by identifying the leaves that can be reached within one single jump. And this is done in this part here. So for J going from 0 up to A.size, we're going to check if A Fibonacci number J minus 1 is equal to 1. In other words, if at position Fibonacci J minus 1 we have a leaf, the array A is equal to 1. In this case, this particular leaf or this particular position can be reached within a jump of a Fibonacci number. We're going to change the value of reach steps array, position Fibonacci J minus 1 to 1. So this position can be reached in one jump. Then we will move on to other leaves. So we're going to go from I equal to 0 up to I A.size. And first we're going to skip the places where we don't have leaves because we're not interested in those. Anyway, these are not allowed positions for the frog. And the reach steps I that are already computed in the previous section here. So if there is something that is positive, like we've already computed for a particular position or for a particular leaf, the number of steps that we can reach this leaf, we don't have to repeat this same operation again. So in this case, we are going to insert the continue order here. Then I'm defining two integers, two variables, the minimum I, which is equal to -1 at first, and the minimum value, which is 100,000, because our problem is limited to rivers within 100,000 of width, as per the description on Codility. Then for j equal to 0 up to the Fibonacci dot size, notice here that we are starting the iterations over all the Fibonacci numbers to check which number will provide us the minimum steps or the minimum jumps in which we are going to reach this particular position I here. So we have for each I, position I, we're going to check all the Fibonacci numbers that we have computed. And for this, we are going to check the previous index, which is equal to the current index minus the Fibonacci j, meaning minus the Fibonacci number we are looking at right now. If it's something that is negative, we are going to break. In other words, if it's negative, it means it's definitely not -1. It's something that is -2 or less. Otherwise, if we didn't break outside of this loop, we are going to look if the reach steps previous I is positive. In other words, if jumping back a Fibonacci number or a Fibonacci distance is going to land us on a leaf that is possibly reached by the frog. So it has reach steps index that is positive. So it's either 1 step or 2 steps and so on. And at the same time, if the minimum value is greater than this particular value, reach steps previous I. So since here we are iterating over all the Fibonacci numbers, but at the same time, we don't want any number of jumps. We want the minimum number of jumps to reach the position. So if these two conditions are verified, we're going to modify the new minimum value, which is going to be our new reach steps previous I, and the minimum index for this particular value, which is previous I. And when we have finished iterating over the Fibonacci numbers, all the Fibonacci numbers, and we have found the minimum number of steps to reach one particular position I, we are going to check the minimum I if it's different than -1. And in this case, we are going to write that the reach steps, the number of steps to reach this position I, is equal to the number of steps that we have found for the previous position plus 1, because we need one more jump to reach this position I, starting from any previous position that we have found. So anyway, you might need some moment, you might need to repeat this part more than one time to digest the ideas here. So when we have filled all of these numbers, we're going to check if reached steps of a size -1, it's the other border of the river, is positive. In this case, we are returning this particular number of steps that is needed to reach that particular position. Otherwise, it means that the frog can't reach this position or the other border of the river using Fibonacci jumps, in which case we are returning -1. In Python, it's the same thing as in C++. However, we had the luxury here to define another function, which is called the Fibonacci n, just to compute the Fibonacci numbers. And we simply sliced out the first two elements that are not needed from the Fibonacci sequence. Then we are moving on with our solution function, taking a list A. We're appending the number 1 at the end of A, which is the other border of the river, just like we have done in C++ solution. And we are computing the Fibonacci numbers that we needed. And we are declaring a new list initialized at 0 at first, which is the reach steps list of the same size of A. So we start by checking the leaves that can be reached within one single step first. We are checking if for j in the Fibonacci numbers, if aj -1 is equal to 1, meaning if it's possible to reach this particular position within a jump of Fibonacci distance. In this case, the reach steps of this position, j -1, is equal to 1. Then we continue our search to check for leaves that can be reached with more than one step, and for I in range up to length of A, meaning for I going from 0 up to the length of A. If AI is equal to 0 or reach steps is positive, we are going to continue, meaning if we don't have any leaves at this particular position, or we have already computed the number of steps and it's positive in this position, we're going to jump and continue. It's not worth repeating the calculation of this for this particular position. Then we're going to define two values: minimum index, meaning minimum position or the position of the minimum, which is equal to -1 at first, and the minimum value of the step or the jump, which is equal to 100,000 for j in the Fibonacci numbers, meaning we are going to iterate all the Fibonacci numbers for a particular position I from the array A, and we are going to check if the previous index, meaning I minus j, is negative. In other words, if this position can't be reached within a Fibonacci distance jump, then in this case we're going to break out of this particular loop of Fibonacci numbers. Otherwise, we are going to continue, and if reach steps previous I is positive, meaning if we have found within a Fibonacci distance a previous leaf that can be reached with Fibonacci jumps, it means that it can be an intermediate leaf to reach this position I that I'm looking at right now. So in this case, if it is positive and at the same time we have a minimum value that is higher than the reach steps previous I, because remember, we are trying not only to reach the position I, but also to reach it with the minimum number of jumps. So if we have a minimum number of jumps that is higher or greater than what we have found so far, we're going to update this minimum v, and we are going to update also the index of this minimum, of this found minimum, which is equal now to previous I, the previous index. And at the end, when we have finished iterating over all the Fibonacci numbers for a particular position I, we're going to check if the minimum I, the minimum index that we have found, is different than -1. If it is the case, it means that we have found an intermediate position that can be reached by the frog, then that can lead to this particular I position. And in this case, we are going to take this the number of steps to reach this intermediate position, and we're going to add one more jump to it to reach the position I. And this is how we're going to fill our reach steps array or a list with the number of steps to reach every particular position I in the array A. So when all of this is done, I mean, when we have done this for all the positions I in the array A, we're going to check if the reach steps length of A minus 1, meaning the last element, which is the other border of the river, has a positive value of jumps, in which case it is possible to reach it with a positive number of jumps. And in this case, we are going to return this particular number of jumps that we have just found. Otherwise, it means that the other border of the river can't be reached by the frog using the Fibonacci jumps, and we are going to return -1 in this case. Okay, this is it for this exercise. I hope you guys had the patience to follow through, because I know it's a difficult exercise. It took me a while. It took me like a week or a bit more to find the solution, to digest the information, and to try to put it into a video. So this is one of these problems that's gonna take you some time. It's gonna put you in some frustration maybe at some moment. Don't get discouraged. Keep up the good work until our next video, and see you next time.